Our planet, Earth, is a remarkable place. Teeming with life, diverse ecosystems, and a rich geological history, it stands as a testament to the wonders of the cosmos. Imagine a cosmic calendar that compresses the entire history of the universe into a single year. In this grand timescale, each month represents roughly 1 billion years, and each day encompasses nearly 40 million years. On this cosmic calendar, our planet doesn't appear until early September, a testament to the vastness of time that preceded our existence. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, a vast cloud of gas and dust, known as a solar nebula, began to collapse under its own gravity. This swirling nebula, a chaotic nursery of cosmic debris, held within it the seeds of our solar system. This newborn star, blazing with intense light and heat, illuminated the surrounding disk of leftover gas and dust. Within this rotating disk, tiny particles of dust and ice, remnants of long dead stars, collided and stuck together, gradually growing larger over millions of years. Through a process called accretion, these cosmic dust bunnies continued to attract more and more material, their gravitational pull increasing as they grew larger.
In the early stages of its formation, Earth was a hot, molten inferno. Constant bombardment by asteroids and comets, remnants from the solar system's chaotic infancy, released tremendous amounts of heat, keeping the planet in a molten state. The formation of the Moon had a profound impact on Earth's evolution. Its gravitational influence stabilized Earth's rotation, preventing wild swings in its axis that would have made the development of life much more challenging. As Earth began to cool and solidify, its molten surface hardened into a thin crust, marking the transition from the Hadean Eon to the Archean Eon, a period marked by the emergence of the first forms of life. Imagine, if you will, a time when our planet was a maelstrom of molten rock and fire. The Hadean Eon, named after the Greek underworld for its hellish conditions, was a period of intense heat, volcanic activity, and cosmic bombardment. Adding to this chaotic tableau, the early solar system was a shooting gallery of leftover debris from the sun's formation. Asteroids and comets, some the size of small cities, rained down upon the young Earth with alarming frequency. These impacts, carrying tremendous energy, generated immense heat, further melting the planet's surface and delaying the formation of a stable crust. One of the most significant events in Earth's early history, and one that would have a profound impact on the development of life, was the formation of the Moon. Imagine, if you can, the sheer scale of this cosmic crash. Theia, hurtling through space at unimaginable speed, slams into the young Earth with the force of 1 billion atomic bombs. The debris from this impact, a mixture of molten rock and vaporized material, is blasted into orbit around the Earth. Over millions of years, this orbiting debris, bound by gravity, gradually coalesces to form our Moon. As the Hadean Eon drew to a close, Earth began to transition from a molten inferno to a more temperate world. The relentless bombardment from asteroids and comets gradually subsided, allowing the planet's surface to cool and solidify further. This period of relative calm marked the beginning of the Archean Eon, a period spanning from about 4 billion to 2.5 billion years ago. The Archean is characterized by the emergence of the first continents, the formation of oceans, and, most importantly, the appearance of the first single-celled life forms. These early landmasses were small and fragmented, constantly reshaped by volcanic activity and the shifting tectonic plates.
Imagine a time when Earth's oceans were not the vibrant blue we know today, but a murky greenish-brown broth teeming with dissolved minerals and organic molecules. This primordial soup, as it is often called, was the crucible in which life first emerged on our planet, a testament to the remarkable power of chemistry and time. One prominent theory suggests that life may have originated in volcanic hydrothermal vents, those fissures in the ocean floor where heat and chemicals spew from Earth's interior. These vents, teeming with energy and dissolved minerals, could have provided the necessary ingredients and conditions for the formation of the first self-replicating molecules. Over time, these molecules may have organized into more complex structures, eventually giving rise to the first primitive cells. From single cells to stromatolites, the first architects of life. The first life forms to grace our planet were simple, single-celled organisms known as prokaryotes. Stromatolites, some dating back over 3.5 billion years, provide tangible evidence of life's early presence on Earth. These layered structures, found in ancient rock formations around the world, represent the earliest known ecosystems, built by communities of microorganisms working in concert. As cyanobacteria spread across the planet, they pumped increasing amounts of oxygen into the atmosphere, gradually transforming it from a toxic brew to the oxygen-rich air we breathe today. The Great Oxidation Event, a turning point in Earth's history. Prior to the Great Oxidation Event, which began around 2.4 billion years ago, Earth's atmosphere contained very little free oxygen. This dramatic shift in atmospheric chemistry had profound consequences for life on Earth. For many anaerobic organisms, those that thrived in oxygen-poor environments, the rise of oxygen was toxic. The presence of oxygen in the atmosphere allowed for the evolution of aerobic respiration, a more efficient way to extract energy from food. The dawn of complex life, from single cells to multicellular organisms. For billions of years after life first emerged on Earth, the planet was inhabited solely by single-celled prokaryotes. One key step was the development of eukaryotic cells, which are larger and more complex than prokaryotes. Eukaryotic cells possess a nucleus that contains their genetic material, as well as other membrane-bound organelles that perform specialized functions. The evolution of multicellularity likely occurred multiple times in different lineages of eukaryotes. The Ediacaran period, spanning from about 635 to 541 million years ago, provides a tantalizing glimpse into the early evolution of multicellular life. During this time, a strange and wonderful array of soft-bodied organisms inhabited Earth's oceans, their fossils preserved in ancient seafloor sediments. The Ediacaran biota thrived in shallow, nutrient-rich waters, their soft bodies sculpted by the currents and waves. These early animals likely fed on microbial mats or filtered organic matter from the water, their simple bodies lacking the specialized organs for predation or complex movement found in later animals. Despite their diversity, the Ediacaran biota ultimately went extinct, their reign marking a brief and enigmatic chapter in the history of life. Following the enigmatic Ediacaran period, the stage was set for one of the most dramatic events in the history of life on Earth, the Cambrian explosion. This remarkable period, spanning from about 541 to 485 million years ago, witnessed an unprecedented burst of evolutionary innovation as life diversified into a dazzling array of forms.
During the Cambrian explosion, the fossil record explodes with evidence of new and complex life forms. Animals with hard shells, skeletons, and sophisticated sensory organs appear in abundance, fundamentally transforming Earth's ecosystems. This period marks the emergence of most of the major animal phyla we see today, from arthropods and mollusks to vertebrates, the lineage that would eventually give rise to humans.
Several factors likely contributed to the Cambrian explosion. One possibility is that rising oxygen levels in the atmosphere, a consequence of the Great Oxidation Event, allowed for the evolution of larger, more active animals with higher metabolic rates. The evolution of predation, with some animals evolving the ability to hunt and consume other animals, may have also driven diversification, as prey species evolved new defenses to avoid becoming someone else's lunch.
The Cambrian explosion was a pivotal chapter in the history of life on Earth. It marked a dramatic shift from the simple, soft-bodied organisms of the Ediacaran to a world teeming with complex, diverse, and often bizarre creatures. The evolutionary innovations of the Cambrian set the stage for the incredible tapestry of life that would unfold over the next 500 million years.
Following the Cambrian explosion, life on Earth continued to evolve and diversify at an astonishing pace. The Ordovician period, spanning from about 485 to 444 million years ago, witnessed a remarkable expansion of marine life, known as the Ordovician radiation. During this time, the seas teemed with a bewildering array of creatures, from giant cephalopods with spiral shells to filter-feeding brachiopods that carpeted the ocean floor.
The Ordovician radiation was a time of ecological innovation, as life explored new niches and developed novel adaptations. One key development was the rise of planktonic organisms, tiny creatures that drifted in the water column, forming the base of the marine food chain. These planktonic communities, composed of algae, protists, and the larvae of larger animals, supported a diverse array of predators, from jellyfish and comb jellies to early fish.
Another notable feature of the Ordovician was the diversification of corals and other reef-building organisms. Coral reefs, those bustling underwater cities, provided shelter and food for a myriad of creatures, contributing to the overall biodiversity of the Ordovician seas.
The Ordovician radiation, however, was not without its challenges. Towards the end of the period, a series of environmental changes, possibly triggered by volcanic eruptions or asteroid impacts, led to a mass extinction event, one of the big 5 extinctions in Earth's history. The Ordovician-Silurian extinction, as it is known, wiped out a significant portion of marine life, paving the way for new evolutionary lineages to emerge.
The Silurian period marked a time of recovery and renewal for life on Earth. New ecosystems emerged, and life continued its relentless march of evolution.
The seas were repopulated with diverse creatures, including brachiopods, trilobites, and early fish.
The evolution of jaws in fish was a significant event. This innovation allowed fish to become efficient predators, driving diversification.
Jaws provided fish with a powerful tool for capturing prey, paving the way for jawed vertebrates.
For billions of years, life on Earth was confined to the oceans. The vast continents, though teeming with potential, remained barren and lifeless. However, during the Silurian and Devonian periods, life began to make its first tentative steps onto land, a pivotal chapter in the history of life on Earth.
The colonization of land by life was a gradual process, involving a series of adaptations to overcome the challenges of a terrestrial environment. One of the first obstacles to overcome was the need for structural support. Unlike the buoyant waters of the ocean, the air provided little support for living organisms.
Plants, the pioneers of terrestrial life, evolved rigid cell walls made of cellulose, a complex carbohydrate that provided structural integrity, allowing them to stand upright and grow towards the sunlight. Another challenge was the need for a means of obtaining water and nutrients from the soil. Plants evolved roots, specialized structures that anchored them to the ground and absorbed water and minerals from the surrounding soil. They also developed a vascular system, a network of tubes that transported water and nutrients throughout their bodies.
Animals, too, faced challenges in their transition to land. One significant challenge was the need to breathe air. Gills collapse outside water, making it impossible to extract oxygen.
This led to the evolution of lungs for gas exchange. Locomotion was another challenge. Animals needed strong limbs and skeletal structures. Early vertebrates evolved from lobe-finned fish.
Reproduction posed a challenge. Eggs and sperm would quickly dry out.
Land animals evolved internal fertilization. This led to the evolution of amniotic eggs.
The colonization of land was pivotal. It opened up vast new habitats and ecological niches.
The Permian period, from 299 to 252 million years ago, was a time of dramatic change for life on Earth. Pangaea's vast interior had extreme temperature swings and arid conditions. Reptiles evolved waterproof skin and amniotic eggs, thriving in dry climates.
Reptiles diversified rapidly, from herbivores to agile predators. Synapsids, ancestors of mammals, were among the most successful groups.
The Permian ended with the most severe mass extinction, the Permian Triassic event. The Great Dying wiped out 96% of marine species and 70% of terrestrial vertebrates.
From this devastation, dinosaurs emerged, marking the beginning of their age. As we conclude our journey through Earth's history, we are left with a profound sense of awe and wonder. From its fiery birth to a vibrant planet teeming with life, Earth's story is a testament to cosmic forces and life's resilience.
We've seen continents drift, oceans rise and fall, and diverse life forms evolve and vanish. Each epoch, from the Hadean to the Anthropocene, has shaped the world we know today. Through gradual change and dramatic upheaval, Earth shows an extraordinary capacity for renewal.
Mass extinctions, though devastating, have paved the way for new evolutionary lineages and greater biodiversity. The rise and fall of species and shifting continents underscore Earth's dynamic nature.
As we face an uncertain future, it's crucial to remember Earth's history and our connection to nature. Earth has endured countless challenges, from asteroid impacts to dramatic climate swings. Through it all, life has persisted, adapting, evolving, and thriving.
Our challenge is to learn from the past, recognize our interconnectedness with nature, and forge a sustainable path forward.